We've seen the definition of what it means for a function to be continuous, but definitions don't usually make a ton of sense until we see some examples. So let's look at some examples and ask ourselves the question, is the function continuous? Here I'm looking at the graph of a function, and I want to ask myself the question, is the function continuous? Specifically, I'll ask myself the question, is the function continuous at the value x equals 2? So I come over here to x equals 2 and I look at what's happening with the function. We remember that continuity means that the limit as x approaches 2 of the function is in fact the function's value at 2. So I ask myself the question, as I approach along the function x equals 2, am I getting the function's value? Well, I have a big dot here that says the function's value at 2 is equal to 1. And if I look very carefully, the function is approaching 1 from both sides. So the limit of f of x as x approaches 2 is 1, and the function value at the point x equals 2 is also 1. So this function is in fact continuous at 2. I could look at all the other points on the function as well and ask myself the question, is the function continuous at every point, which is the same as, is the function continuous? And I can see that the graph of the function doesn't have any other interesting features, right? These arrows mean the function continues along without any interesting features. And so I have this nice smooth line that I can draw without picking up my pencil. So my guess would be that yes, the function is continuous at all those other points. I would have to actually calculate the limits and make sure that they work out if I was checking to see that the function was continuous at every point. But the graph seems to indicate that everything is good. Here's another example. I asked myself the question, is the function continuous? Here, I'm interested in the specific value of x equals 1. So let's look at what happens at x equals 1. Well, the limit as x approaches 1 of f of x, well, I look at this graph and I see here from this side I'm approaching 1, and this side I'm also approaching 1. So the limit as x approaches 1 of f of x is equal to 1. On the other hand, there's a hole in the graph at 1, and the function's value is up here at 3. So f of 1 is actually equal to 3. Since 1 is not equal to 3, this guy is not continuous at 1. Again, I could look at what's happening everywhere else and ask the more general question, is the function continuous? The answer is still no, because I can find a value where the function is not continuous. But all of the other values, again, the arrows indicating that nothing really interesting is happening beyond those points, every place except 1, I could say that the function is continuous, but overall, the function is not continuous. Here's a third example. Again, I look at the graph of this function and I ask myself the question, is the function continuous? Here I'm interested at the particular value of x equals 2. So I ask myself the question, first, what is f of 2? Well, I can come over here to x equals 2, and the dot is up here at y equals 2, so the function value at 2 is 2. But what about the limit as x approaches 2? Well, the limit as x approaches 2 of f of x, from over here on the left-hand side, it looks like I'm approaching 2, so I'm feeling pretty good about myself. But if I come over here from the right-hand side, it looks like the function is approaching -1. And since -1 and 2 are not the same, we say that the limit as x approaches 2 of f of x does not exist. And if the limit does not exist, then it certainly can't be equal to 2. So this function is not continuous. Again, Because the limit does not exist, the limit is not equal to 2, and so by the definition of continuity, the function is not continuous at x equals 2. Our first couple of examples were all about what the graph of a continuous function looks like or doesn't look like. What if we're just presented with an algebraic definition of the function? Here's our second example. Again, we ask ourselves the question, is the function continuous? This time, I'm going to be interested in the specific value of x equals -2, but we'll again talk about general values of x. So first, again, continuity means that the limit as x approaches -2 of f of x should be equal to f at -2. So, first let's ask ourselves the question, what is f of -2? Well, I plug in the value -2 everywhere I have x, so f of -2 is -2 squared plus 3. This guy happens to be +4 plus 3, or 7. So the limit as x approaches -2 of f of x, we want to be equal to 7. So let's check it out. What is the limit? Well, the limit as x approaches -2 of f of x is the limit as x approaches -2 of x squared plus 3. We know that the limit of a sum is the sum of the limits. So I get the limit as x approaches -2 of x plus the limit as x approaches -2 of 3. This better be x squared. Limit as x approaches -2 of x squared plus the limit as x approaches -2 of 3. Now, I know that if I have an exponent on my x value here, that the limit of a power is the power of the limit. We can call this the power rule. So I get limit as x approaches -2 of x squared plus limit as x approaches -2 of 3. Okay, well, the limit as x approaches -2 of x, this is just x, so I can plug in -2. And here, this is a constant function. So I have -2 squared plus 3, which is again equal to 7. So, f is continuous at -2, as we expected, right? This function, x squared plus 3, is a polynomial. So, we discussed last time that polynomials are some of our favorite functions because we can just plug in the value instead of going through all this limit nonsense. So, in general, can I prove that this function is continuous everywhere? Well, I would like to know that the limit as x approaches some value a of f of x is the limit, is not the limit, is f applied to a. Well, I have the limit as x approaches a of x squared plus 3 is equal to, since this is a polynomial, a squared plus 3, which is in fact f of a. So, this f is continuous for any a, or f is continuous everywhere. This is a general statement about polynomials that we can also prove. If f is a polynomial, we have already seen, this was last week, that the limit as x approaches a of any polynomial f is equal to, I just plug in the value for a. This means that what we actually showed last week is that every polynomial is continuous. What a nice fact. Finally, let's look at a function that might or might not be continuous depending on some parameters. Our third example is completely different. Here I'm asking myself the question, is the function continuous? And I'm concerned about the function being continuous everywhere. So I have this piecewise defined function, which means that I have to figure out whether it's continuous on the first piece, on the second piece, and at the point where the two join together. I have too many variables here, right? Normally I'm plugging in x's, but I also have these k's that are hanging out in my function. And so the real answer to this question is maybe. If we choose the correct value for the k. All right. So looking at this top part of the function, no matter what value of k I plug in, this is the equation of a line. Some coefficient times x minus 1, so this k is telling me the slope of the line, and minus 1 the y-intercept. And since lines are a special case of polynomials, we know that this piece of the function is continuous, as long as x is less than 3. Again, here I have x plus 2k, which is the equation of a line. So again, this piece of the function is also continuous, as long as x is greater than or equal to 3. So the only interesting point is what happens at x equals 3. Well, on this side, this function is approaching, because this is continuous, this is approaching what would happen if I plugged in x equals 3. So the limit from the left, x being less than 3, is k times 3 minus 1. Remember, again, this is a continuous function, so I can just plug in x equals 3. So if I simplify this a little bit, this is 3k minus 1. The limit from the right is, well, again, we said this is a continuous function, so I can just plug in x equals 3. So this would be 3 plus 2k. So the first thing that I need is that I need these two limits to be equal. In the first example, we saw that if the two limits aren't equal, then the function can't be continuous. So I need these to be equal. All right, so let's set them equal to each other. We had 3k minus 1 from the left, and we had 3 plus 2k from the right. Now I solve for k. So I add 1 to both sides. 3k equals 4 plus 2k. I subtract 2k from both sides, and I get that k equals 4. So if k equals 4, the function could be continuous. In this case, the function looks like f of x equals 4x minus 1 when x is less than 3, and x plus 2 times 4, which is 8, for x greater than or equal to 3. Okay, and we've just seen that the limit as x approaches 3 of this function, f of x, is equal to 3 plus 8, or 11, from the right-hand side, and 4 times 3 minus 1, 11, from the right-hand side. Since these are equal, the limit exists. We also know that f of 3, well, I come over here to my piecewise function. 3 is included on the bottom part here, so that's 3 plus 8 equal to 11. These guys are all the same. So if k equals 4, f is continuous. If k is not equal to 4, then we don't have that these left and right hand limits are the same. So in that case, the function is not continuous. So the answer here really is maybe. We can make the function continuous by choosing a good k, or we can make the function discontinuous or not continuous by choosing a different k than 4. Okay, we've considered continuous functions from a bunch of different angles now, and even talked a little bit about why polynomial functions are continuous. Make sure you do some practice exercises on this topic, and if you have a question, post it on the forum.